First of all, a very warm welcome to the hardcore IT professionals who made it until to the last session. We'll be talking about Windows Server 2012 Hyper-V Networking Evolved. And my name is DJ van Hooyen. I work as a technical architect for the AGIF in the Netherlands, which means Agentschap voor Geografische Informatie Vlaanderen. And in that function, I have to kind of move around a lot of data for very demanding users. Basically, that means I'm very interested in anything that can help me do that. So, what are we going to talk about? Well, what's new in Windows Server 2012 in networking that's changed or improved or new, and how it relates to Hyper-V where possible. And why do we want to talk about this? Well, basically, we all have the same problem. We have to meet very demanding business users who want their applications up and running. And they want this with high availability, continuous availability, and also you have a tendency to have multi-tenancy. You have people who want security. They want to be able to extend their networks. So basically, they are demanding a lot. Then the second problem is CAPEX. It shouldn't cost a lot. So then you want to leverage everything you have and get the most out of it. So basically what you'll see then is things like network virtualization, quality of service, bandwidth management, all things that relate to converged networking because you want to use what you have for multiple purposes to optimize the cost. But then you have to deal with performance and scalability. Can you get enough throughput? It's a challenge. And then last but not least, all those things tend to be complex. And if they're complex, they cost a lot of money. And it's also the enemy of high availability. The more complex something is, the more chances you'll have something will go wrong. And in the end, this is the eternal challenge we have. And not just for networking, because even if Microsoft would succeed in taking away every bottleneck, wherever in the network stack it is, you have three other resources you have to deal with. I/O, CPU, memory. If you don't take away the bottlenecks over there, you're just going to hit it. So basically in Windows Server 2012, all the efforts they did in the networking stack, they had to match it in all the other resources to deal with the cost, to get high availability, to give you the capacity you need and performance. So what does that mean, networking-wise? Well, you have to address, let's say, bottlenecks in the host. You have to deal with bottlenecks in the hardware, being the network cards or the switches and the routers. And more often than not, you'll see that you don't have to address only one of them, but it's always a combination of one or more. A lot of the times, all of them. So, before we continue, does anybody know what NUMA is? Oh, that's pretty good. K-group, kernel group, stuff like that. We'll shortly address it just to make sure we all know what we're talking about. So basically, you have a processor, which is today a socket with multiple cores, basically. Now, non-uniform memory architecture, NUMA, means that you have an amount of memory that can be accessed really fast by a number of logical processors. That's a NUMA node. And basically, that's what you want. Because if your processor has to run to some other memory, it takes longer and you take a performance hit. You all know what a core is? Well, a NUMA node exists out of multiple cores, and a core itself can exist out of multiple logical processors. Think hyper-threading in the Intel world, where you have two logical processors, even if you have only one core. And then there's the kernel group. Well, basically, Windows can handle only 64 processors. So if you have more than 64 processors, what do? You group them, you call it a group, you create a second group of another 64 processors, and that's how you scale up your processors. Why is this important? Well, if your networking stack isn't aware of these principles, how can they take them into account to leverage them? They can't. So you'll see this is used everywhere. Receive-side scaling. I guess everybody knows what it is, and even if you don't know what it is, you are all using it. So let's dive in and see what it does. Well, basically, it makes sure that all your incoming network traffic, the handling of it, the interrupts for it, are spread across the CPUs. Now, this is very much necessary, more so today than ever before, because we are seeing ever bigger CPUs in a server. You used to have a couple of cores, now you have 8 cores, 10 cores, and it's only going up. So if you have huge machines and you can't deal with all those cores, you're going to be in trouble. Because if you don't have RSS, there's one CPU handling all the interrupts for the incoming traffic. You don't want that. But then you have the new things, NUMA nodes. RSS needs to be aware of NUMA nodes. It is now in Windows Server 2012. It needs to be aware of kernel groups, K groups, if you have really large hosts. This will help you. What it also couldn't do before was deal with UDP traffic. It can do that now as well. And what you see for applications where incoming traffic is really high, like backup medium servers, certain types of web servers, file copies, this makes a tremendous difference. So basically, this is what you don't want. A server with a lot of cores and only one being used to handle the receiving traffic. This is very bad. What are all those processors doing? Nothing. So here's a picture from our real production environment. This is one of our backup servers. And as you can see, all the cores are very hard at work dealing with the incoming backup traffic. And it's a rather significant amount of backup traffic as well. So I've tried to create some animations to explain certain concepts. So let's try. This is what used to happen in the days before Windows Server 2012. And what you see is that, indeed, multiple cores are used to handle multiple network queues. The problem is, you're not using everything. So we need to fix this. Now, this is what we have. Packets are coming in, and they're evenly distributed across all the processors. I hope this is still running. Yeah, OK. Across all the processors, and you don't really waste one. And that's why you have to be NUMA aware, because it would be silly to send traffic linked to a certain process to memory that's not directly accessible by that core, because then you have a performance overhead. So once you start doing that, you need NUMA awareness. And you can take the same concept further. Once you have multiple kernel groups, you have to be able to handle that as well. And basically, that's what's possible now. So that's RSS for you, and it works magnificently. But there's one thing you need to take into consideration with receive-side scaling, and that is the fact that it gives you one queue, one processor per session. So one session comes in, gets a queue, goes to a core or logical processor. Second one comes in, goes to a queue, goes to a second logical processor, and so on. And that's how you get your distribution of usage. Keep that in mind. We'll need it later. There's another beast, receive segment coalescing. And basically what it does is it takes the incoming packages and it puts them in a memory buffer and creates a larger package. Why? Well, one of the overheads TCP/IP has to deal with is the fact that you have to handle all the headers of a package again and again and again. So why not combine them into a single larger package and only take that overhead hit once? And that's exactly what it does. Now, it can't go higher than 64K. Anybody knows why? It's the largest size a TCP/IP package can have, basically. Normally, it reduces CPU overhead with 10 to 20%, which is quite nice, because we're talking about network improvements in relation to Hyper-V. That's 10 to 20% CPU cycles you have to run your virtual machines. And in case you didn't know it, if you have some 10 gigabit cards, go have a look. It should be enabled by default. And it just works out of the box. The animation, well, packets comes in, they all get sent to the buffer, and when the buffer is full, or you have reached your highest package size you can, they will be processed in one interrupt, and that's it. Instead of 8 interrupts, only 1. So there's the load reduction on your processors. Dynamic virtual machine queue. Anybody heard of that? Anybody used it in the past with Windows 2008, R2? No, nobody got bitten by it? Okay, cool. What it does, actually, it's basically, you have to think of it as receive-side scaling, but then for virtual machines. Because you have another issue. If you don't have VMQ, all the traffic going to the virtual machine has to be handled by a core, and it will be only one. And there we go again. There's one core that will become your bottleneck. You do not want this. So what you need to do is use multiple cores. And again, 10 gigabit Ethernet cards, almost always enabled by default. Why is this so important with 10 gigabit? Well, the processors were more than powerful enough to handle anything 1 gigabit could throw at them. But when you bring 10 gigabit into the picture, this becomes ever more important. But there's more. It's now also a dynamic process. So let's have a look at how it works. What you see here is how basically a Hyper-V virtual switch works. So let's use the pointer here. You have network traffic coming from the wire, going to your virtual switch. Into the parent partition, you have to deal with routing, filtering, data copying. Then it goes over a port to the VM bus, up into the virtual NIC, to your virtual machine. So basically, there's a lot of work being done here. What if you could offload all that work to your network card? Then you get this situation. Basically, all the routing and such is handled now in the card, and it just flows right through to the VM bus, straight into the virtual machine. And the good news is, the interrupts handling this path are spread across all the processors you define that are to be used, which is cool. And now there's even more in 2012. It's dynamic. So what do we mean by dynamic? You define a certain number of processors to be used with VMQ. Now, if you don't have VMQ, it's very easy, 1. So now you have VMQ. This is what you had in Windows 2008 R2. You assign a number of processors to handle the interrupts. If you have multiple network cards, you can use multiple different processors to do so, but it's fixed. And this has a cost, because using all those processors, the coordination of that process also takes some effort, and it has to be worthwhile. So if you have not enough network traffic to, let's say, make that overhead worthwhile, you're out of luck. You're actually reducing your level of enhancement you get from it. So in 2012, they've made it dynamic, which means it will use as many as you have defined when it's needed, and it will drop back to lesser processors, hence lowering that overhead to make sure you always get the best possible performance. That's what VMQ and dynamic VMQ can do for you. Microsoft says turn this on by default. It is always turned on by default, and you can leave it that way unless you run into trouble. But normally it should work. There is a lot of confusion about it. In the early days, the queues you had were limited, which means if you enabled this for every virtual machine, the virtual machines are served on a first-come, first-served basis. So what you get, a machine gets a queue, another machine gets a queue, other machine gets a queue. Perhaps they don't use that queue. Perhaps they don't have much incoming traffic. And then the other machine that also wants to get a queue, you get an event log entry out of queues. So they told you, beware, enable it, but do it wisely. Hand them out, don't hand them out like candy to everybody. Well, now the problem should be going away, because most modern NICs support 64 queues, and in the future only more. And I don't know about you, but I don't see too many people running more than 64 virtual machines on one host, right? Then there's another beast. It's called single root virtualization. And basically, this gives you a direct path from the hardware into your virtual machine. Because let's say you are interested in virtualizing your SQL servers, but they have a tremendous amount of I/O. Or you want to use an application that relies on real-time data exchange with very low latency. And you don't want to risk losing a packet. So what could you do here? Well, if your NIC supports it, and again, most modern 10 gigabit NICs do, but Windows didn't up until now, you can use single root I/O virtualization. Basically, your NIC has two functions. The physical function, well, that deals with the hardware part of it, the PCIe commands and that sort of stuff. The virtual function is something that it will assign to a virtual machine, and once that happens, the data traffic will flow from your physical NIC straight into your virtual machine, which is great, because you lower the CPU usage that you used to have on the routing, the VLAN filtering, etc., etc. It provides for very low latency, gives you high throughput, and, well, you're in business. There's a couple of conditions you need to address. Your BIOS has to support it, your CPU has to support it, you have to have the correct chipset, but if you buy a modern server, even the previous generation servers of the big vendors, they all have this support. So that's not really a showstopper here. And then there's something that Microsoft did very well here, and that is live migration. What if I told you you could have this feature, but you can't live migrate? It's a bit of a bummer. Now, Microsoft has solved this issue. So how do they do it? Well, we know how SR-IUV works, so let's look at it again. We assign our virtual function to our virtual machine. Once that's established, you go away from the normal software path to the virtual switch, and the data goes straight into the virtual machine. So that's the flow. Basically, this is SR-IUV in action. Now you want to live migrate. How are you going to live migrate this? Once you move that virtual machine, you're going to lose the connection. So what does it do? Well, it goes back to the software path. So basically, the software path will be stopped, the virtual function will be removed, and then your virtual machine will go to the next node. If it finds that everything is available to restore SR-IUV, it will assign a virtual function again, and there we go. The NIC is assigned, and the data flow goes from the hardware straight into the virtual machine again. Now this is nice. This is nice because there's nobody else who does this. The competition might say, well, it's only a marginal use case, but I kind of like the fact that if I have a marginal use case, I'm supported. And it becomes better. You can do this even if your host you have on this side doesn't support SR-IUV. It will just remain in that software mode. You can do so with NICs from different vendors. So there's nothing stopping you from live migrating using SR-IUV from a host that has an Intel NIC to a host that has a Broadcom NIC. It even works if they are on different firmware, which is kind of unusual for networking features. Usually they're quite difficult about what version of firmware you have, and they all have to be equal. Well, with SR-IUV, it's quite easy to do. Another biggie in Windows Server 2012 is NIC teaming. So this is one of the scenarios where everybody is extremely happy. And why is everybody extremely happy? Well, because it used to cause a lot of headaches. We as customers were dealing with way too many issues supporting this, getting this to run, and especially keeping this running. Then again, the NIC vendors, they would like to help us, but there are so many different permutations, there are so many new networking features coming out. It was a game of always installing the latest firmware and drivers, and that was far from easy, especially in a virtualized environment. And then Microsoft had a statement that, well, basically this is hardware supported, so you have to go to your hardware vendor, not to us. Now they would try to help you, but basically if you could make it work without NIC teaming, you were out of luck. So nobody is sad to see it go, because all the things you needed to do with Intel and Broadcom to get it to work are something of the past. It's not that they will disallow you to use third-party NIC teaming solutions, and in some cases you might want to because they offer special functionality, but Microsoft has just about anything on board to handle whatever you can think of. And if you really need something special, you can always go to the vendors. So we're not going to talk about this too much because NIC teaming is a session on itself. But you can go switch dependent and switch independent. And the nice thing here is you can go active-active. And why is active-active nice? Well, it used to be dependent on your switch configuration, LACP, that sort of stuff. And now it doesn't. You have active-active and switch independent configurations, which is one thing I like a lot about this. They have all the normal load balancing options with address hashing, and of course a special one when you're using Hyper-V, that's called the Hyper-V port mode. You have different types of hashing, 4-tuple, 2-tuple. Can you use the MAC address? Can you use the IP address and the MAC address? It all depends. Well, it's all in there in the stack. Anybody who plays or knows a lot about NIC teaming will recognize all these features, and you can implement them. Now, it does come with some warnings. Some of the advanced features in network cards, once you team those network cards, they can't be exposed on top of the team because they are hardware features. So, how to solve that? Well, here's an example. Normally, you would team 2 NICs, and then you would create a virtual switch on that team NIC, and then you use that virtual switch to assign network traffic to your VMs. This is the way to go because you only need to team once, and you don't have to deal with multiple NICs in your VMs. Easy. Unless you want to use SOIUV, because it's not exposed. So in that situation, you won't team them. You will just create a virtual switch on top of each NIC, and you'll team in the guest, because teaming is also supported in the guest. You might wonder why. Well, this is a scenario where you want to use this. By the way, if you want to play with NIC teaming, you can do so with NICs of different vendors. There's nothing stopping you. Some people even like that, because if you have a driver issue with an update from one vendor, if your team consists of NICs from different vendors, you still have connectivity. You can even mix better. You can mix speeds. You can team a 10 gigabit one and a 1 gigabit one, but that's only for testing. You don't want to do that in production. It will work, but it's not supported, and it's ill-advised, let's say. You can do all kinds of fun stuff. I think you can go up to 32 team members, which should be more than ample for most environments. And then we're going to jump into SMB Direct. Now, there is a new beast in Windows Server 2012, and that's called SMB 3.0, and there is something phenomenal about it. It absolutely blows everybody who looks at it away. And that's, again, another session, but there are 2 very important things with networking I want to discuss here. And the first one is SMB Direct, or SMB over RDMA. And basically, this is what you need if you want enormously high throughput with low latency and without overloading your processor, because everything is offloaded to the NIC, and things get done in kernel memory. Basically, what can it do for you? It takes away all the TCP/IP overhead out of the Windows machine. It offloads it to the NIC. And there are different types of RDMA. There's the iWarp, which is basically putting TCP/IP into the hardware. There's ROCE, they pronounce it in America. It's RDMA over Converged Ethernet, which is pure Ethernet, not even TCP. Pure Ethernet on the machine, which is very performant, but it does require DCB on the switches, and we'll look at that later. And then there's InfiniBand. And it's funny to see, because InfiniBand was something that was really out of the picture with normal IT people, and now I see more and more people beginning to look at InfiniBand again. So it's quite funny to see that one. So basically what it does, let's say you have to move a package between 2 servers, between a client and a server. If you want to read the data from the disk, then you have to put it into the TCP/IP stack. It gets translated in X amount of TCP/IP packages. It puts it over the wire. It has to assemble it again, and then it has to persist it to disk again. What if you could just say with such a card, you know what? I need that data, and here's the memory where you can write it to. And the NIC cards, the network cards, do the copying at a lot larger package sizes than TCP/IP can. It's 512K, not 64K max, while the most used package size is 1,500 and 9,000, around 9,000 if you use jumbo frames. Well, look at the difference. And it's all done by the hardware, meaning it is very fast, has low latency, and very low CPU overhead. And again, all those resources you save can be used by your Hyper-V host to do what it needs to do, that is, serve up virtual machines. This is for performance. Now, if you combine this with another beast called SMB multi-channel, then you have the best of both worlds. This will give you aggregation of bandwidth, meaning if you have multiple pipes, you have more throughput. And it gives you redundancy, because if one of your pipe fails, it will auto-detect this, but it will keep going over the remaining one. So basically, you have redundancy with multiple NIC ports without using teaming. And you have bandwidth aggregation. And it's even better. Remember what I said about receive-side scaling? One session comes in, one queue goes to a core. Second session comes in, queue goes to the second core, and so on. So you needed multiple sessions to be able to use all your cores. What if you have one giant long-running session? Well, this will leverage RSS and create multiple connections even if it's a single session. So this is pretty cool. Let's have a look at what it does. Example 1. What we see here is 10 gigabit network card with receive-side scaling enabled, but no multi-channel. So you have one session, one core will have to handle all the incoming traffic. Why? Well, they can't be leveraged. There is no multi-channel. This is pure RSS. RSS, one session, one queue, one core. Now go to multi-channel. It will leverage RSS, and it will use the queues to create multiple connections for one session. So even with one huge session, you will leverage your cores. This is nice. Let's take a look at the second example. What will happen if we have multiple NICs but no multi-channel? With RSS, without RSS? Well, basically, this is what you know, right? Nothing will happen. You have one session, one connection. Multi-channel into the game, aha, we have RSS, and we have multiple NICs. You will have multiple channels between two NICs, but you have multiple NICs, so even more channels, all for one session. This is nice. Look at the amount of bandwidth you can get there, especially if you start thinking about 10 gigabit cards, especially if you start combining this with RDMA. This is better than fiber channel, people. Interesting. Well, what if you don't have RSS enabled? As you have multiple NICs, at least you will have one connection per NIC. So even then, you have a benefit. Teaming. Is this compatible with teaming? Absolutely. You might ask, why do I want this to be compatible with teaming? We have failover already, you told us so. Well, as it turns out, NIC teaming, the failover of it, is a bit faster than it is with pure multi-channel. So if that is important for your application, you might consider teaming and perhaps combining both of them. Because, as you can see, this works perfectly. Here you see a team, well, no multi-channel, it will only use one path, one connection. If you team, you have RSS, it will use multiple connections over multiple team members. And if you don't, it will use the multiple team members. And then the Valhalla of throughput, basically, RDMA. Now let's look at an RDMA card. And do you notice something special? There's no multi-channel here, but these cards are RDMA capable. Basically, you need multi-channel to leverage RDMA. It is multi-channel that will pick up on the fact that your card is RDMA capable and will start to leverage it. If you don't have multi-channel, even if your cards have RDMA and everything is configured correctly, no joy. If you do have multi-channel, hey, you start out with a little TCP/IP connection, multi-channel detects you have RDMA, and now you're in the realm of the big pipes, right? That's what the big red dots lines mean. It's really huge throughput. And that little TCP/IP connection lingers around, just in case something goes wrong with the RDMA. This is your fallback connection. Auto-configuration. If you add NICs to your server during a copy process, the NIC will be detected and used. Similarly, if you remove one, you won't lose your connection. The session will still be running. Same for wireless and wired. If you are running wireless and copy a lot of files, you think, this might go better over a wired connection. Just plug it in on your laptop or whatever. Why? Well, It will detect that you have an extra connection. It will detect, hey, this one is better than my wireless. I will use that one. What you cannot do, and this is what this picture is demonstrating, you cannot mix technologies. It will detect which one is best, and it will use it. By default, out of the box. You can mess around with it as much as you want with PowerShell, configure it to your heart's content, but be careful. Just start out with the defaults, look where that gets you, and you'll be fine. And if you really do need to intervene, do it wisely. Some more network features that are very interesting and very important. Perhaps one of the most useful ones, the first one you will see when you install Windows Server 2012, is this one. This is a picture from my Generation 12 Dell server. What do you see? The nicknames actually match the names on the hardware. There's no more pulling out the cable to know which NIC port goes where. You know, this is nice. I like it. And as you can see, these are the online NIC ports. This is an add-on card from Intel. It uses the same method of identifying them. So it takes out the guessing and the plugging and unplugging of cables to find out what is what. It's very simple, and it's long overdue, I might say. What else do we have? DC TCP, data center TCP. What kind of beast is this? Well, this is a slide from Microsoft. Basically, you have a low buffer switch. They call it the cheap switch. Well, in terms of 10 gigabit switches, yes, they are cheap, but you might not really consider them cheap budget-wise. Now, what you will see is that the buffer will be depleted, and you will get into some sort of a stop-start scenario, just like basically a traffic jam, right? So what does Windows Server 2012 do? It has intelligence. It knows how much buffer is being used and how much congestion there is on the network. So it can adapt to it. It doesn't just react by the fact that it can't send any more packages. No, it knows how the congestion is, and it will throttle the amount of package it sends on the network. Now, what does this do for you? It means that your switch, even with low buffer, will perform a lot better because you're not stopping and starting all of the time. What do you need for it? Well, it's called explicit congestion notification, because remember, somebody or something has to tell your server, hey, we have congestion, act accordingly. So that's what your switch needs to support. And it only works where it makes sense. And this is a screenshot from our data center. Basically, the ones where you see applied setting data center is where the data center TCP is enabled. And these are actually our cluster networks. And as you can see, it is not enabled on the port we are using for RDP because it doesn't make any sense there. It's for east-west traffic, as they call it, not north-south. It's within the data center. So you go from this, and you all know what this is, you're way too familiar with it, to this. You get a green wave, and you have a traffic control center. Basically, Windows 2012 in combination with enhanced congestion notification or explicit congestion notification. So that's how you should think of it. Then we enter the realm of, let's say, data center bridging. Now, this is a very nice beast, but it's also the most complex one. It's one that normally Windows administrators, hypervisor administrators are not used to dealing with, because your operating system has to be able to deal with it, your network cards have to be able to deal with it, they are the converged network adapters, as they say, and your switches have to support it. Now, it's very nice because it can provide a tremendous amount of throughput. And basically, this is what you need to make RDMA work, or at least one type of RDMA, the wacky one, the RDMA over converged Ethernet. Now, if you want maximum throughput, this is what you'll have to do. If you don't, and you are more than satisfied with what IWARP, TCP/IP offloading on your NIC can do, you won't have to deal with this. But basically what it does, it reserves bandwidth for particular types of traffic. So it prioritizes that traffic. And it also assures minimum bandwidth. Why? Because you don't want priority traffic to starve all your other traffic, because that wouldn't be healthy. But it is the way to lossless TCP/IP or Ethernet. And that, again, where would you use this? If you think about SMB 3.0, multi-channel, RDMA, and you might have heard that you can now use a file share as storage for Hyper-V or SQL Server or IIS. This is where this comes into play. So basically, you could think of it as a carpool lane, right? You have reserved lane for that particular type of traffic. So whatever happens to the guys on the other lanes, you have your spot to have decent speed and arrive on time. Now, you don't want to starve these guys, and that's where the minimum bandwidth comes in. And that's what you'll see if you look at what DCB requirements are. You need enhanced transmission selection, which is actually the minimum bandwidth. And you need priority flow control, which is actually saying this is priority traffic and that can use the reserved lane. That's what you're doing. There's two optional things. One is the DCB exchange protocol, which is basically that you have the capability of having your network cards and your switches talk to each other and agree upon what kind of DCB configuration they have. If you don't have that feature, you'll have to define everything manually and make sure it's equal over the entire stack. And you can also enhance this with congestion notification, so your operating system can take that into account as well. But it's not required, it's an option. Now, this was quality of service for converged networks, hardware. You can also do it in software. You have quality of service. You've had it before in Windows via group policies on the host. Now you have quality of service for the Hyper-V switch. So you actually can create a NIC team, as is demonstrated here, create one virtual switch on it, attach your VMs, but hey, you can create new virtual NICs and use them for live migration, for storage, or for management. And of course, as everything is going over the same team members, what if you're live migrating? Do you want your live migration traffic to push out all the other traffic? No, you don't. So what you'll do is you'll set minimum, maximum bandwidth, either with a value, really truly in megabytes, or with a weight, how much percentage-wise of all the available bandwidth can one of the networks get. Now this is very nice, and I advise you to play around with it and learn it, because you have many options on how to do it, and sometimes this will be the best and the most simple choice you can make, but you have to take something into consideration. The NIC teaming. We all know that SRUV isn't supported by NIC teaming, so are you going to do this or not? Depends on your scenario. By the way, RDMA is also not exposed on top of NIC teaming. Multi-channel is, RDMA is not. So you need to think about it. And what you also need to know is that you shouldn't mix different mechanisms of doing quality of service. Because you do the same thing on multiple layers and you might actually lose performance, and you might also get into a very complex environment where you don't know why things aren't working because you don't even know where it's happening anymore. So choose one, implement it well, and enjoy the benefits, but don't use everything because you think you should, because it's in the box. There's one thing very important. We said that we didn't want to starve all traffic that's not prioritized, just like in the DCB example. Well, on a default switch, you have the same principle. You might say, I give priority with X amount of minimal bandwidth to a certain type of virtual machines. You can do that, and you leave all the others alone. You don't define anything. But what would happen? Minimum bandwidth is minimum bandwidth. What if they want more? They would starve the other virtual machines. So there is what they call a default bucket, that you can give a weight, so they get an amount of traffic that can't be taken away. Otherwise, you would starve them, and you don't want that. So where would you use this? Well, perhaps you want to play with scenarios where you have a virtual machine like a gateway that goes out to the internet. You don't care about what's happening in your network. You're on 10 gigabit. None of your virtual machine uses all the bandwidth available, so have a ball. But outside, well, that costs money, and perhaps you want to throttle that machine. So you can say, hey, on this NIC, I want the maximum bandwidth to be that amount, so it will never exceed 100 megabytes. Things like that. You can define SLAs on virtual machines. You could say, hey, this is the maximum bandwidth a virtual machine can have, but you can also say this is the minimum it should have. And then you can start handing out SLAs to your internal customers. You can also throttle a virtual machine. Perhaps you have an application that tends to take away all the bandwidth. Well, put a cap on it. You can do it now. But again, think about it and don't do it on all levels. This is just a screenshot how easy you can apply it to one virtual machine. Is this advisable? Some people hate this. Some people prefer to work with PowerShell and assign weights instead of amounts. Because if you start doing this with amounts, how are you going to deal with live migrations to another node? How are you going to deal with the fact that you might be handing out a lot more minimal bandwidth than you have? So it has its use case, but be careful in how you use it and where you use it. Another very nice feature we have now, and that's due to the extensible switch we now have in Windows Server 2012, you might have heard about that, is the HTTP guard and router guard. Basically, you can now say with a checkbox mark or with a PowerShell command, that virtual machine will drop any DHCP packet. So if you're in a college environment where everybody is playing around and perhaps installing DHCP servers, how many of you would like it if your users installed DHCP on a virtual machine and brought it into your network? I guess most of you would say, that causes a bit of problem. Well, just set that setting and they can't do anything wrong anymore. The same thing with routing. Perhaps you want to prevent that somebody sets up a router and sends packages to destinations that are really not, let's say, welcome or allowed. Block it. You can do it now. And in box, you have port mirroring. You can say, hey, this little VNIC has to send all its traffic to another VNIC, which is then called the source, the target, sorry, on another VM. So you can say, hey, VM A, this port, it's a mirror. Another VM where you install a network sniffer, you define that as the target. And all the traffic is duplicated. So you can have a look at what's going on in a virtual machine. Now this is basic port mirroring. You can't do anything with protocols or ports, TCP/IP ports. You can if you buy third-party extensions to the Hyper-V switch, but in box this is something you never had, and which is quite useful. IPsec task offload is not a very nice thing we have. Why is this important? Well, let's say you are in a business that is regulated, and you need to have IPsec. It's a security policy, you can't work around it. Now, the nice thing is that IPsec could be offloaded to the NIC. And if you're dealing with hardware, that does it for you. But we're talking about virtualization. So all those CPU cycles that IPsec consumes have to be dealt with by the Hyper-V host, i.e. you lose a certain number of cycles you can't have for your virtual machines. So to save money and to get better performance, you should be able to offload this as well, and now you can. So you can really just say with a little checkbox, enable IPsec offload, and if your hardware supports it, it will work. I think it even checks it automatically if it detects that your NIC has that capability, which is also quite nice. Then there's another little beast, which I find very interesting, that's the port ACL. Basically, you can set rules on a VNIC, which is actually a port on a virtual switch, and say what it can do. You can block all traffic coming from a virtual machine, NIC, or port, to your entire network, except perhaps one virtual machine, or where it can talk to. Certain applications, perhaps, or certain environments, you might not want them to talk to a certain network segment. Perhaps, what if people configure something wrong? What if people put their servers on a network they shouldn't put it on? How can you block it? Well, you can configure the switch ports, and you can say, you can't talk to that machine. You can use wildcards, you can exclude ranges, and you can accumulate or, let's say, combine rules. You can say, I block all traffic from this NIC to wherever in the network. But I will allow this NIC to talk to that IP address. So you can combine them. And a third implementation of port echoing is actually what they call counters. And counters are very interesting, because instead of saying you can't go there or you should go there with allow or deny, you're saying that the action is count. And count is something you need if you want to do monitoring, metering. So this is the basis of chargeback. This is the basis of showback, even if you don't want to charge internally, but at least you have some data to show to your manager, look, those guys are really the ones that are consuming all the bandwidth, so perhaps they should pay a little more, even if you can't charge them on a monthly or a weekly basis for what they use. It all depends on your environment. And all the virtual switch security functions are based on this. This is, let's say, the building block of all security features you'll find in an extensible switch. So I've left some time for questions and answers. I have tried to show you where in the networking stack Microsoft has addressed its resources to make Windows Server 2012 one of the most performant networking versions they ever had. We've implemented it very early after RTM, and we're already reaping the benefits for our backup servers, for live migration, for all kinds of scenarios. So I can tell you from personal experience, this all does work. So if you have any questions, feel free to ask them. Thank you very much.